In our previous lessons, we were learning about atomic structure and spending a lot of time on the structure of the electron cloud. Now we're going to start learning about the periodic table. And the periodic table is arranged the way it's arranged because of this atomic structure. Let me sort of go back and review a little bit and kind of bring you up to speed where we are. We've been doing this for several lessons now, looking at subatomic structure. We started out by looking at what you should have learned in physical science about subatomic structure, at least as far as the electron cloud, and that you learned in physical science that there was a layer. It's actually a spherical sort of shape where you have up to 2 electrons, and then you have a next layer which is up to 8 electrons, and these are called energy levels. Now sometimes in older books, and sometimes teachers even refer to it that way, as shells, but shells, I don't know, maybe that's not the best way to refer to it. It's not really a problem if you understand that shells aren't really shells like seashells, but it's more like a part of a cloud, okay, kind of a region, statistically speaking, where those electrons are found. The next level, our primary energy level, can hold up to 18 electrons, and the fourth can hold up to 32 electrons. Now, that doesn't mean that there are going to be that many in those levels, but that's how many it can hold up to. That's what you learned in physical science. Now we're learning, and you learned this several days ago, and we did balloon models for this, that within these energy levels, it doesn't occur in the first energy level, but starting in the second energy level, these electrons sort of arrange themselves into regions within that energy level. So electrons, if the tip of my fingers are electrons, I guess I could draw little E negatives on the end of my finger to show you, but if the end of my fingers were electrons here, then normally they wouldn't want to be close to each other because like charges repel, and electrons are all negative. But what happens is they have opposite spins, and that opposite spin allows it to negate the electromagnetic repulsion of those electrons, and so you can get 2 of them together. So pairs of electrons then can be arranged in these regions, or are arranged in regions like this, because that gets them in regions that are separated from each other. They're not pushed apart so much. So they're attracted by the nucleus in the center, but the repulsion doesn't push them completely out. It allows them to stay in that same region. That's why we have these orbitals. And so s orbitals are spherical. So in the second primary energy level here, or the third primary energy level here, you'd have an s orbital that looks like this. Inside that would be a lower s orbital, and inside that is another lower s orbital if there is one. And then you also have these p orbitals, which are double balloon shapes, but not really the middle part, only the top part. Okay? We went through all that. And we learned how to do orbital notation to sort of give addresses or a kind of, I think of it kind of like census data, but you guys might not know what I mean by that. It's just kind of a list of people and their information about them. Well, that's kind of what this does. These do, actually all of these do. So orbital notation, we organize these to show how many electrons are in each orbital and so forth. So in the first energy level, this represents what an orbital is. It's not what an orbital actually looks like. It's only representing the placement of electrons in that first energy level, in that s sublevel, in this orbital that the square represents, and so forth. So you build up to that to get the complete orbital notation for an atom. Then you can sort of condense that a bit and write an electron configuration where the boxes no longer appear. In fact, the electrons aren't separated out into orbitals as they are here. They're just added up. So here we got sp6, 2p6, where here we're showing all 6 electrons. Here we just have a number. So you have to infer where those electrons are and what their orientation is, up or down spin. Those arrows representing up spins and down spins. I know those look like L's and 1s, but that's kind of a half arrow just for space. Then we further condense the electron configuration down to this, because we really only care a lot in chemistry. We care about the other things too, but mostly we care about this outer energy region here. And so when we condense the electron configuration down to this this noble gas version, then we sort of take out the part that is corresponding to the next lowest noble gas. So krypton's electron configuration goes from 1s all the way up to 4p. Okay, so we take all that out and condense it down just to the symbol in a bracket. And so that just gives us the part of the atom that we most care about, or the part of the electron cloud we most care about in chemistry. Once we get there, then we can count the number of electrons in the highest energy level, 4 is not the highest energy level. 5 is the highest energy level. In 5, there are 2 electrons, and so we write electron dot formulas here for that. And these electron dots are going to become part of how we figure out how to put 2 or more atoms together to make molecules. It's part of what's called the Lewis structures we're going to write. And those are really important in how we understand how to figure out the way that molecules go together. Okay, it's kind of like the beginning place for it. So that's where we're headed. So we're not going to do the bonding of atoms together in this unit. We're going to talk a little about how bonding occurs just a little bit. We're not going to get into the actual bonding part. That's the next unit. Okay, so that's bringing you up to the current point, and now we're ready to get out your homework and exchange your homework paper so that we can grade your homework from yesterday. If you'll exchange your homework paper with another student, or if you don't want anybody else to see your paper, you can have me grade it. So the homework that's due today, we were supposed to write orbital notations, both kinds of electron configurations, electron dot formulas, and then ion formulas for 2 elements. And the first one was calcium. Okay? And so calcium, you had to have the symbol for calcium, the colon for calcium, the box with the arrows correctly oriented, one up, one down. The first one has to be up, the second one down, and it has to be labeled 1s. The second box here, same thing, box, arrows, orientation, labeled 2s. Then 3 boxes with all the arrows, correct orientation, labeled 2p. Then 3s, box, arrows, orientation of the arrows, 3s. 3 boxes in 3p. Okay, so you have correct orientation of the arrows, 3 boxes, labeled 3p, and then 4s, 1 box with 2 electrons because calcium is in the 4th primary energy level, and its electrons, it only has 2 electrons in that 4th level. Those are both going to be in s. So you're going to get 1 for the symbol, 2 for the colon, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 points for all this. Okay? So that's your orbital notation for calcium. Then you're going to condense that for the full electron configuration. It looks like this. So each of these groupings are going to get a point. So calcium and the colon still get points, but you get groupings sp2. By the way, that must be a superscript 2, not a subscript 2. Superscripts are raised above the line, not dropped below the line. Superscript 2, superscript 2, superscript 6. Okay? If they have 2p and a subscript 6, none of that counts. All right? It's got to be a superscript 6. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 point here. That's the points for that complete electron electron configuration. Yes. And then we're going to take out the noble gas. The noble gas starts at 1s and ends at 3p. So we're taking all that out. That noble gas is argon. Argon goes in brackets. The brackets are worth a point. The symbol for argon is worth a point. And then 4s2 is worth a point. That's a total of 5 points. Okay. Then we're going to write the electron dot notation. There's only 2 electrons in the highest energy level. You can look at any one of these 3 formulas and see that. 2 electrons in the highest energy level. So I'm going to give you a point for the symbol and a point for each of the dots. The dots don't have to be on the top and the right. The tops can be on the left and bottom, but they cannot be on the same side. Okay, they have to be on different sides. All right? And so that's 3 points. And then once you remove the dots, then you're going to have a 2 plus charge. Electrons have a 2 negative charge. Calcium has a total of, 20 protons? Is that right? Yes or no? Nobody knows. Not good. 20 protons. So we had 20 electrons when it was an atom. We removed 2 electrons, and you're going to get a 2 plus charge. Electrons are negative, protons are positive. If I have 2 more protons than electrons, then I'm going to have a 2 plus charge. Got it? And so the symbol, number, and plus sign are all worth points. You must have the plus sign. You can't say calcium 2. Plus is a charge. It doesn't tell you where it appears on a number line. Okay? It's an actual charge. That's why we put the plus after the 2 and not before it. All right? So 2 plus is what's required for points. All right? So altogether, all of this is worth 37 points. You with me? Everybody good? All right, then let's go to the next element. Arsenic. Same basic idea for grading. We've got the 3D sublevel here. We're in 4S. For arsenic, then, the 3D sublevel drops back one primary level. So we start out in 4. When we get to the D sublevel, it drops back one primary level. So this is 3D. Okay? And so in arsenic, you're going to have those 4 single electrons in 4 single boxes over here. If they put 2 electrons together here, that's wrong. If they have an empty box over here, that's wrong. You don't give them those points. Okay? Got to have single electrons in those 3 boxes over there. So single electrons in those, a total of 28 points for everything for the orbital notation for arsenic. Okay? Now, we're going to condense that down to an electron configuration, a full electron configuration. Remember, the symbols and the colons are worth points. Add everything up, you get 10 points for that. All right, and then we're going to condense that then further to show the noble gas version of this electron configuration. The noble gas happens to be the same, and it starts at 1s and ends at 3p. So we're going to take all this out. So when I say it's the same as what we had up here. We took out everything from 1s up to 3p, and for argon, we're doing the same thing here. So all of this right here, up to 3p6, gets condensed down to the symbol argon in brackets, and then 4s2, 3d10, and 3p3 is what you have on the end of it. And so when you count up everything, element symbols a point, colons a point, brackets a point, argon symbols a point, 1, 2, 3 more points, that's 7 total. Okay? Then for the electron dot formula, we just count the electrons in the highest energy level. The large numbers are designating what the energy level is. The primary energy level is designated by the large numbers. So in level 4, you have 2 electrons in S and 3 electrons in P. That's a total of 5 electrons in the highest energy level. So we need 5 dots, not 15. In fact, you cannot go over 8. Got to remember that, or you should remember that. Okay, octet rule. We don't want to go over 8. There are actually cases where we go over 8, but we're not going to deal with those, at least not right now. Okay. All right. So you're going to have 1 electron on 3 sides and a pair of electrons on 1 side. And which side you have that pair on, I don't care. It could be left, right, top, bottom. It doesn't really matter as long as you have single electrons on 3 sides and a pair of electrons on a 4th side. Okay. And so we're counting all the dots as a point, the element symbol a point, for a total of 6 points. Okay. All right then. In order to get the ion symbol, then we want to, in both the case of calcium up here and with arsenic, we're trying to arrange things in the easiest possible way, simplest possible way, to get 8 electrons in the outermost level. That's following what's called the octet rule. Okay. And so instead of taking away, say, 2, 3, 4, 5 electrons, it's easier to add 3. That's a smaller number. So when I add 3 electrons, I'm like pairing up 1 here, and pairing up 1 here, and pairing up 1 here. And what you get is this right here. Okay? So that's an ion symbol, and that's one of 2 acceptable ion symbols here. If you got this, if you're going to show the electrons, and you don't have to color code them, like me. I color code them to show where I put in the extra electrons. If you're going to show electrons, everything has to be in brackets with the charge on the outside. Add 3 electrons. Electrons are all negative. That gives you a 3 negative charge. Arsenic, the atom, had 33 protons and 33 electrons. This arsenic has 36 electrons. So 3 more electrons than protons. Electrons are negative. That gives you a 3 negative charge. This is also an acceptable formula for the ion of arsenic. Just AS, capital A, has to be clearly a capital A. Okay? Don't make it a little a that's just big. Make it a clearly capital A and a small letter S. And the only way you know an S is small is by comparing it to a capital letter. It must be roughly half the size of the capital letter. If they have a capital A and a capital S, that's not the correct formula. Okay? So those don't count. That doesn't count. That doesn't count. None of these symbols count unless you have a capital A and a little s. So you get 3 points from the symbol for the element, the number 3, and the negative sign. You've got to have all 3 of those things to go at all 3 points. Okay. All the points together for calcium is 37. All the points for arsenic is 54. All the points total, 91 for this assignment. Okay, so you're going to add up all the points and put the total points they earned in a square center top of their page. You know, despite what high school students, I'm sorry, I can't talk today. Despite what high school students think they can do, it's obvious to me that high school students have difficulty dual tasking. Okay, that everybody seems to think I can do 2 things at one time. Well, I guess what? You can't. Okay. All the research shows that when you try to dual task, you end up missing half of both things. Okay. But when it comes to atomic structure and its relationship to the periodic table, you kind of got to do that anyway. Somehow you got to be able to figure out what the atomic structure is and also what the periodic table arrangement is and how the 2 of them go together. Okay? The periodic table is set up the way it's set up because of atomic structure, particularly because of electron structure. Okay, now we put the atoms in there in order of their proton number, which is their nuclear structure. But except for the fact that we put them in numerical order for their arrangement from left to right, we're putting them in columns because of their similar chemical behavior, and that similar chemical behavior comes directly from their electron cloud structure. Okay? And so it's important to think about, it's really important to think about the electron structure of the atom when we're talking about why atoms are in the columns that they're in and why that allows us to figure out patterns of behavior over the periodic table. Okay? So that's what we're going to be working on today, are patterns on the periodic table. We could say this is periodic properties. If you want a title for what we're doing today, it's mostly about periodic properties. Okay? Periodic properties. Now you have handouts in front of you, if you're in class here, that look like this. So you've got 3 different periodic table outlines to be able to do notes on. Okay? And so you're going to be taking notes in this section. I'm going to be doing on a big table so you can kind of see. See, I've got the elements kind of lightly behind it, so you can kind of see what pattern we're looking at here. All right. So first thing I want to look at is where the metals, nonmetals, and metalloids are located. Okay? Metals, nonmetals, and metalloids. Okay? Metals, nonmetals, and metalloids. On your large periodic table, you can see this stair step here, right? And you probably already know from physical science, if you remember this, that everything over on this side are metals, and everything up on this side is made of nonmetals. Okay? But there's more to it than just that. I'm going to draw in this stair step, and I'm going to include the left side of boron in this stair step. On your blank outline that I gave you, you should be drawing in this stair step on metals, nonmetals, and metalloids. Okay? All right. Now, when we were talking about S, P, D, and F sublevel regions, we said that helium was not best placed right here. We said that we're talking about S sublevels. Helium really belongs over here where the S sublevel is located. These first 2 columns were the S sublevel. Remember that? And we've already done that periodic table. You should already have that information in your notes. So I'm not going to go back over S, P, D, and F sublevel regions. You need to know that, though. Okay? That's one of the patterns you need to know. But it turns out that when we're talking about metals and nonmetals, it's hydrogen that's poorly placed. Okay? So hydrogen really doesn't best belong right here. Okay? Hydrogen best belongs over here next to helium. When we're talking about SP and F sublevel regions, helium goes over here. But now we're talking about metals and nonmetals. Hydrogen goes over here. In fact, if you look at some periodic tables, like this one in your packet, for oxidation numbers, hydrogen's over here, as well as over here. Okay? And the reason for that is hydrogen, for the most part, behaves a lot more like a nonmetal than it does like a metal. Okay? So it best belongs over here when we're talking about nonmetals. Now, having said that, one of the weird things about hydrogen, I love the weird stuff about elements, it's cool to me, okay, is that, theoretically speaking, that scientists believe that this is true, people who know more about it than I do. If you get hydrogen under enough pressure, it will behave like a metal. How much pressure do you ask? Nobody asked, but I want to say it anyway. I want to answer it anyway. You're going to ask? Okay, thank you for doing that. I appreciate it. All right. So, how much pressure? Well, like the kind of pressure you have near the rocky core of Jupiter. Huh? Oh, it's huge. It's really huge, okay? I mean, we're talking about hundreds of times more pressure than we have in this room right now, okay? Got it? So really a lot of pressure. All right. So this area over here, then, these are the non-metals. And this area over here, these are all metals. Everything over here is metals, except for hydrogen, of course. And even down here, these are all metals, too. All right? Now, right along the stair step, and the reason that I included the extra step on the line here and this one over here is because I want to make sure I'm clear about what makes up what's called metalloids. If I touch the stair step that I drew here on two sides, except for aluminum, well, that and whatever this unknown yet to be named element is down here, these are all metalloids. Okay? These are all metalloids. Okay? What are metalloids? Thank you for asking. No, nobody asked me, but I'll answer it anyway. Metalloids are elements that sometimes behave like metals and sometimes behave like nonmetals. Okay? They're extremely important. Electronic devices, computers, radios. Huh? Yeah. Microwave. Well, yeah, I'm not sure. Probably microwaves, but I'm not so sure whether that's the case or not. But you know, most of the electronic devices you guys all carry around with you all the time, well, those require that you have metalloids to make them work. Okay? And we won't get into it in this class why that works, but it's basically, it's the behavior of this metal, sometimes non-metal, sometimes behavior, that makes those work. Now, it's also a lot of other kinds of metals in your electronic devices, but that's one of the primary things that makes it work. Right? Okay, so that's really all you need to know about metals, nonmetals, and metalloids for now. Okay? It's really important that you remember hydrogen belongs over here when we're talking about metals and nonmetals. Got it? All right, then. Next thing I want to talk about is about atomic size. Now, atoms are super, super, super small. The width of this marker point here, and of course my marker is a little bit bigger than your pencil point probably, is about 1 millimeter wide. Okay? If I take that and slice it in 1,000 pieces, I get a distance of about a micrometer. Okay? If I take that micrometer and slice it into 1,000 times, then I get a nanometer. And I have to cut that into about 10 pieces to get the size of about an atom. Okay? Or that's the size unit of measurement we use for measuring atoms. So we're talking about really, 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 really small. Okay? But atomic size does matter sometimes, okay, despite how small it is. But there's some funky things about the way that atomic size arranges itself when we're trying to figure out how it fits on the periodic table. And we can figure out the size relative one atom to another based on where it is in the periodic table. Now, hydrogen over here, if you look on your periodic table, and I hope you have your periodic table out. I did ask you guys to have that out. All right, here's hydrogen and helium, okay? I've connected it with this little red line here. As I go from hydrogen to helium, I want to know what the relative sizes are. Now, hydrogen has one proton, if you look on your periodic table. Wouldn't be a bad idea. On your periodic table, hydrogen has one proton. It has a mass of slightly more than 1. Helium has a atomic number and therefore 2 protons, atomic number of 2 and therefore 2 protons, and has a mass of a little over 4. Okay? By the way, the mass is actually in atomic mass units, okay? Atomic mass units. And the symbol for atomic mass units is a lowercase letter u. But, so this is about a mass of 4 and atomic number of 2. This is 1 and 1 roughly. So which one of these two atoms is larger?
Helium.
That would be the most likely response. It's not true.
I meant hydrogen.
Okay.
On the left.
Okay. All right. Most people think that helium's larger. Okay, can't take it back now. You said it that way the first. You said helium was larger the first time. I'm sorry. Anyway, here's why. Remember that stuff when we first started talking about all these structures, and we talked about what you learned in physical science about the way the atom is arranged? Let me find that. All right. Electrons are held to the nucleus by protons in the nucleus. Electrons are held to the nucleus. Electrons are negative. They're held to the nucleus by protons, which are positive. If I have in this energy level right here just one electron and only one proton in the nucleus, that's not as much pull as having 2 protons and 2 electrons. Does that make sense? Yep. Yep. Okay? If I have more protons and more electrons in the same energy level, there's more force pulling it together. That shrinks the electron cloud. So the fact that I have 2 protons and 2 electrons in helium shrinks the electron cloud of the atom over hydrogen, which has only 1 electron and 1 proton. You with me? And so hydrogen, if we compare the size of the electron cloud, is larger than helium. That make sense? So as we go from left to right, we get smaller. All right? Now, if we go from hydrogen down to lithium, then we're adding an extra energy level. See that? Only 2 electrons can fit down in this lower energy level. The next electron has to squirt out to a new level. All right? Well, if it's going out to a new energy level, because I can only get 2 electrons there, and it has to do with their opposite spins, you know all that stuff, right? Then I'm adding an extra layer that makes lithium larger than hydrogen. Okay? So lithium is going to be larger than hydrogen. All right? Larger. Okay? But in this second row, if I add a second electron and another proton, second electron, another proton, I've got more to pull it in tighter. You with me? Okay? And so beryllium is smaller than lithium. If I put a third electron out here and another proton in the center, in the nucleus, that's something else that can pull it in tighter. Boron is smaller than beryllium. Carbon is smaller than boron, and so forth. And so in this row, as we go from left to right, becomes smaller. Huh? Well, your lines don't have to be perfect. You just have to have notes. All right, then we go down to sodium. Well, guess what? With sodium, we're adding another energy level. We get bigger sizes again because we have to go up a level. Now, something else is happening along with this that I need to sort of stop for a second and talk about. Okay? And that is what's called the shielding effect. The reason why this pattern occurs is because of something called the shielding effect. Let me see if I can explain the shielding effect to you in a simplified way that if you've never heard it before, you might be able to at least get an idea of what it means. You need to have an idea of what it means, okay? All right. How many of you, anybody here a Star Trek fan? No Star Trek fans? Man, that just breaks my heart, I'm telling you. All right. Star Wars, well, Star Wars, you know what? Star Trek has so much more stuff I can help to explain chemistry with than over Star Wars. All right. This layer of electrons sitting right here, this first layer of electrons, those electrons are moving really, really fast, approaching the speed of light. Okay? Now, I explained to you guys that when we have electrons flowing down a wire, so I've got electrons moving in this direction, okay, down a wire, so this is a wire, that it creates an electromagnetic field. And the flow of the electricity is in the direction of my thumb. The electromagnetic field is in the direction of my fingers. It's called the right-hand rule. Okay? So moving electrons create an electromagnetic field. Got it? Well, these electrons in this first energy level are moving really, really fast. They're creating an electromagnetic field. And it creates a kind of an electromagnetic shield. Okay? It partially prevents protons in the nucleus from holding on to electrons in the next level. Okay? Every time I've got a layer of electrons, it partially prevents the electromagnetic attraction of the protons to the electrons from sort of pushing its way through. It restricts it. Okay? It's an electromagnetic shield. And so one of the reasons why atoms get larger as you go to the next energy level, as you start to add electrons to the next energy level, as in adding electrons to this next energy level when I go to sodium, is because of the shielding effect. And then the more electrons I add to that energy level, so as I add more and more electrons to this level, there's more and more electrons here, more and more protons here for the protons and electrons to be pulled in. That's the idea behind the shielding effect in a real simplified form. Make sense? Okay? And so the shielding effect is the explanation for why it is that atoms get smaller as you go from left to right, larger as you go from top to bottom. Okay? Smaller as you go from left to right, larger as you go from top to bottom. So this row with sodium, they get smaller going left to right again. Smaller from left to right. Smaller from left to right. Smaller from left to right. Okay, but larger going from top to bottom. Alright? The overall pattern then, if I look at everything that's here, the overall pattern is going to be, well, let me tell you about this part here in the middle here, because I really probably should not have put that line all the way through there. Because in this D sublevel, if you remember, when we got to that D sublevel, when we're adding electrons to make the electron configuration and orbital notations, this stuff in the middle dropped electrons into lower energy levels. You remember that? So there's not much effect here at all. I've only got a dotted line. That's a really small effect at all. There's almost no effect at all of having these electrons in this region. You understand? Huh? You should be taking your notes in pencil, guys. A what? Okay, so not much effect there in that D sublevel. Now, the overall pattern then means that the smallest atom is going to be helium, and the largest atom is francium. Okay? And so overall the pattern looks something like this, where we get smaller going up here and larger going down here. Okay? And that's all due to something called the shielding effect. So that's atomic size. Okay? Let's move on. Okay, for ionic size, when we were doing electron configurations, and particularly with orbital notation, well, for both really, because we figured out that in order to make these ions we were doing, that when we reached that point where we had 4 electrons in the outer energy level, that's sort of the break point for whether you give up electrons or gain electrons, remember? Yeah. Okay? And so the column of elements with 4 electrons in the primary energy level, the valence level, the outer energy level, is this one right here where carbon's at the top. Alright, so this is the column with 4 valence electrons. Okay? Now, you need to know, or I need to remind you, that we are super simplifying things in high school chemistry, okay? Some of the things I want to tell you, are not completely true because I'm trying to get you to understand a pattern.
So you're lying to us.
I'm not lying to you because I'm telling you up front. 4 valence electrons. Valence, V-A-L-E-N-C-E. Now, what you're going to find out is when you take the next level chemistry class, and maybe it's in college before you get there, the pattern isn't exactly what I'm showing you now. I'm showing you this pattern because I want you to understand the reason why. The underlying reason why, okay? And we're not going to get so far into why that you can understand where things get off of this explanation, okay? So I don't want to confuse you too much. I'm trying to give you the simple explanation. You can get the more deep explanations later, all right? For right now, I want you to know why the type of behavior we're talking about occurs. Now, if I lose 1 electron from let's just say, let's start with lithium here. I'm going to lose 1 electron. Lithium, the atom, has 3 protons and 3 electrons. If I lose 1 electron, and everything in this column tends to lose 1 electron. They've only got 1 electron in the outermost energy level. Okay, they all tend to lose 1 electron. If I lose 1 electron, then this shielding effect thing, okay, here's the nucleus here. There's 3 protons, only 1 electron out here. If I lose that electron, well, that atom's going to be smaller. Make sense? Yes? If I have beryllium right next to it, if I lose 2 electrons, that whole level's gone. That atom's smaller. And the extra protons I'm adding is shrinking this initial energy level anyway. Okay? I'm getting rid of all the electrons in the outer energy level with metals, and because I have more protons in the nucleus as I go from left to right, it's shrinking down even to whatever the next lowest energy level is. Okay? So, this column of elements then is going to be smaller than the corresponding atomic size. The column of ions here, all these ions, are smaller than the corresponding atom. Okay? All of these are smaller than their corresponding atom. All of those, smaller than their corresponding atom. But because as we go down, we're still adding an energy level, it's still getting larger as we go down. Okay? Each of these ions are smaller than their corresponding atom because we removed electrons. But the resulting ions still get larger as we go down because we still have added an extra energy level. Okay? So for sodium, I removed the one electron from this level, I'm down to this level, but it's being pulled even tighter than the atom because of the extra protons. When I go down to the next element here, potassium, I remove the one electron from this level, but even this level gets shrunk down a little bit because it got an extra proton. Well, that pattern goes through all the way across here, because in this column, I'm also removing 2 electrons for every element. Got it? No. But even though I've removed electrons, I'm adding protons that go from left to right. So adding protons from left to right is still shrinking the size of whatever ion we have as we go from left to right. So ion size is actually going down just as it did before. It's going smaller from left to right. Okay? Smaller from left to right. And larger as we go down. Okay? And so that pattern continues. Larger going down, smaller across to the right. But notice where the pattern kind of stops on us here. You see that? Where am I stopping this time? No, not the same place as before.
Oh, you're stopping at the 4 valence electron.
Right. So I'm stopping at that point where instead of removing electrons, which I do for all these metals, I would be adding electrons over here. Does that make sense?
Yes.
Okay? When we did this with electron configurations, orbital notation, and the electron dots, we were adding electrons with these elements, taking away electrons with all these elements. Okay? So what happens over here, if I have nitrogen, for example, locate my periodic table, there's my periodic table. Nitrogen has 7 protons, and the atom has 7 electrons. What do you think is going to happen to the size of that atom if I add 3 extra electrons to give it all the electrons it wants to have a full outer energy level? What do you think is going to happen to the size of nitrogen? If it is going to go up if I add extra electrons. Okay? It's going to make it much larger. So nitrogen gets way bigger and then gets smaller. Way bigger and then smaller. Okay? And this phosphorus is for the same reason going to get way bigger and then smaller. And arsenic is way bigger and then smaller going down to bromine and so forth. All right? So what we do is we get a jump right here in size. Okay? A big jump. Got it? That says jump. What? Which ones? These over here? Now we're going, those really don't matter a whole lot. Okay? In fact, this section in here really doesn't matter a whole lot. And you know why? Because we're not removing electrons from the d sublevels. For the most part. There's a small amount of difference, but not a lot. I told you to take your notes in pencil. If it's in pencil, you erase. You have an easier time if you do it in pencil than I do with this pen. Well, you know what? My life would be a whole lot less fun if I couldn't give you a hard time. I don't know. You may use a restroom, yes. I hope you can, because it would be really uncomfortable if you couldn't. All right, all that makes sense? Okay, let's move on to our next periodic property. I'm thinking ahead about what I'm doing here. Okay, electronegativity. Oh, electronegativity. Okay. Yes. I can't even hear you. When the person that's gone now comes back, you can go to the restroom. Oh, you want to go to the nurse? Okay. Electronegativity. Let me give you the definition for electronegativity. Well, first of all, let me tell you a little about what electronegativity deals with first, and then I'll give you a definition, okay? So, when you were taking physical science, you were probably taught that there were two kinds of bonding between atoms. Anybody? What? Covalent and ionic. Good. Now, electronegativity primarily deals with covalent bonding. Electronegativity primarily deals with covalent bonding. If we were to look up electronegativity on the internet, you'd probably find some pretty good definitions of electronegativity. Here's a pretty good one. Okay? Electronegativity is the measure of the tendency of an atom to attract a bonding pair of electrons. Well, that's one definition. Let me tell you, okay? I like to think of it like this, that, well, first of all, covalent. Co means, what does that prefix co mean? Together, or two, right? All right. If I have two electrons, and valent means they come from the outer energy level of an atom, valence level, right? Remember that term? Okay. So what it means is I am sharing two electrons between two atoms, right? Electronegativity then is a relative measure of how strongly that pair of electrons is attracted to each atom. Electronegativity is a relative measure of how strongly that pair of electrons is attracted to each atom. So, if I have two atoms and the electrons are shared in between, we looked at how the structure of the atom and looked at how electrons are in orbitals. I was trying to find my drawing of that. Okay, so if you remember, we talked about the structure of the atom. We said there were these sublevels and orbitals within the atom, right? And those electrons are in those orbitals, okay? Well, if I'm sharing an electron between two atoms, I'm not just sharing that electron, I'm also sharing the orbital. Okay, that's important for you to remember. When we get to bonding later, it's going to make a huge difference in your understanding of the way that bonding works, because bonding means we are sharing not just two electrons, but sharing the orbitals themselves. Okay, we're overlapping two orbitals. So the two orbitals from two different atoms become one. Two become one. Wow, that sounds familiar somehow. No, come on, that's from most marriage vows. Give me a break. So these orbitals, if I'm going to share electrons between this atom and another one, those orbitals actually get shared. Okay? And we'll talk about that more later. So covalent means we're sharing electrons between two atoms. Electronegativity is a relative measure of how hard one atom holds on to, or grabs hold or pulls on those electrons it shares with another. Now, the pattern of electronegativity works like this. Fluorine is the most electronegative element. Fluorine is the most electronegative element. There is no electronegativity for the noble gases. Remember, the noble gases already have a full 8 electrons in their outer level. The valence is full. The valence is full for noble gases, this last column over here. So this last column over here has virtually no electronegativity. We're going to just ignore any electronegativity that there is in the noble gases. Okay? Then, because fluorine is so small, and there's almost nothing shielding those outer electrons from the nucleus of fluorine, then fluorine is going to be the element with the greatest amount of electronegativity. Okay? It's the largest. Francium down here is going to have a lot of shielding effect. It has relatively fewer protons in the nucleus than other atoms do in between. So overall, the pattern of electronegativity is highest at fluorine and lowest at francium. But in that D sublevel region, there's kind of no difference there. Okay? There's not much difference in that region. All right? So it's higher over here and lower over here. All right? Electronegativity. The next pattern we're going to look at is first ionization energy. First ionization energy. First ionization energy. So we looked at how to make ions yesterday, right? With ions, we either removed electrons or we added electrons, yes? Okay. When you were taking biology, most students in my chemistry classes take biology first, you may have been taught about how energy is given to muscle fibers for them to actually do what they do. ATP and ADP, remember that? Okay. And you may have, and my apologies to biology teachers, but here's the deal. When you were taught that little phosphate that pops off the ATP, okay, gives away energy, I'm sorry, but that's wrong. Okay. It can. Now listen to me. Listen to me carefully. This is important in chemistry. Anytime you break something, you break a bond, like with that ATP being broke off of ADP, or the phosphate being broke off of ATP, making ADP. If you remove that, it takes energy to make that happen. And so the actual removal of that phosphate requires energy to be put into the system. Now what happens after that is where you get the energy. So you get energy overall, but the actual breaking it off you have to put energy in. Now, that's important because that's how you need to understand first ionization energy. First ionization energy is, definition, first ionization energy is the energy required to remove the first electron from an atom. The energy required to remove the first electron from an atom. So you're going to have to put energy into the atom to get an electron out. Okay, the first ionization energy is the energy required to remove that first electron from an atom. To remove that first electron from an atom. Now, the element that is the hardest to remove an electron from is helium, because those two electrons are closest to the nucleus, and there's two protons, which is one more than what hydrogen has. So helium, there's no shielding effect to speak of, so helium is going to be the hardest to remove an electron. It's going to have the highest first ionization energy, and francium down here is going to have the lowest. And all this stuff kind of in the middle kind of doesn't change a whole lot in there, just like before. Okay? But these noble gases are part of this pattern. You can remove electrons from a noble gas. So it's highest up here and lowest down here. Okay? Yes. Sure. We only got about 6 or 7 minutes before the bell rings. Really? All right. The flip side of that, first ionization energy is the energy required to remove an atom. Remove an electron from an atom. Electron affinity is kind of the opposite of that. Okay? So if it takes energy, if you have to put energy into an atom to remove an electron, what happens if you're going to put an extra electron on an atom? Come on.
I thought you couldn't add stuff. They can only take away.
No, you can add stuff. We added electrons to make ions, right?
I thought you were talking about adding atoms.
No, we're going to add electrons to an atom. If I have to put energy into atoms to remove electrons, what's going to happen if I put electrons onto atoms?
You're going to add ions.
If I have to put energy into an atom to remove an electron, what happens when I put an electron on an atom? Energy's going to come out. So electron affinity then, by definition, electron affinity is the energy that is released when electrons are added to an atom. Electron affinity is the energy released when an electron is added to an atom. The energy released when an electron is added to an atom. Now, noble gases won't accept electrons. That's because they already have 8 valence electrons. They're full, they're happy, they're done. They won't accept electrons. So there is virtually no electron affinity in the noble gases. That's important. You've got to understand the structure of the noble gases. They already have a full 8 valence, a full 8 octet. Their octet is full. They don't want any more. They don't want any extra electrons. No more electrons. Okay. So then, the atom that has the highest electron affinity, the one that gives away the most energy when you add an electron to it, is fluorine. And the electron that gives away the least energy when you add an electron to it is francium. And again, the D sublevel region pretty much doesn't change. So electron affinity is highest over here and lowest down here. But there's no electron affinity for the noble gases. Does that make sense? Okay. The concepts underlying ionization energy, electron affinity, and electronegativity are the same. But ionization energy primarily deals with ionic bonding. Electron affinity primarily deals with ionic bonding. Electronegativity primarily deals with covalent bonding. Okay? You got that? Say what? Ionization energy and electron affinity primarily deal with ionic bonding. Other concepts you need to know to understand ionic bonding. Okay? On the other side of things, electronegativity is a subject that primarily deals with covalent bonding. You got that? Now, I am not going to assign a specific homework tonight, but listen, I gave you 6 periodic properties, and there's one periodic property we've already learned about, the SPD and F sublevel region, right? No. Oh, I thought I talked to you last week. Anyway, the point is, you need to study these. These are going to have to be memorized. Study these over the weekend. Okay? That's your homework. Make sure you understand and understand these patterns and these arrangements of the periodic table. Okay?